fine good morning to everyone. This is Jakudipti of Branch Aeronautical Engineering Semester 6 pairing roll number 2395 Today I am here to give a presentation on behalf of AIT Tech Talk. The subject is Machine Learning Techniques and Practices. The topic which I have chosen is Multi-Source Plume Tracking via Multi-Agent Reinforcement Learning under Common UAV Fault. Then getting into the introduction, plume tracking refers to the process of locating the source of a chemical, biological, radiological or gaseous emission by following concentration gradients in the environment. This problem is highly relevant in applications such as environmental monitoring, industrial leak detection, disaster response, battlefield, chemical threat detection and search and rescue missions. In real-world scenarios, plumes may originate from multiple sources, exhibit turbulence and intermittent behavior, and exist in dynamic environments with uncertain wind conditions. These complexities make plume tracking a challenging task for traditional deterministic control approaches. Unmanned aerial vehicles have emerged as effective platforms for plume tracking due to their mobility, flexibility, and ability to access hazardous or inaccessible areas. When multiple UAVs are deployed corporately, they can explore large areas faster and locate multiple plume sources more efficiently. However, coordinating multiple UAVs introduces challenges related to communication, control scalability, and fault tolerance. To address these challenges, Multi-Agent Reinforcement Learning (MARL) has gained attention as a powerful framework for enable autonomous corporation decision making among multiple UAVs. The multi-source plume tracking problem is in multi-source plume tracking, the objective is to identify the locations of several emission sources based on local sensors, measurements of plume contraction. Unlike single source problems, multiple plumes may overlap, merge, or interfere with each other, making gradient based methods unreliable. UAVs must collectively explore the environment, distinguish between different plume signatures, and converge towards individual source while avoiding collisions and redundant exploration. The problem is further complicated by environmental unnecessity, including fluctual wind direction, turbulence, obstacles, and sensor noise. These factors make plume dynamics high chaotic, necessitating adaptive and learning based approach rather than fixed rule strategies. Motivation and significance is accurate plume source localization is critical for environmental monitoring and disaster response. Multi-agent system enhance coverage and robustness in dynamic and uncertain terrains. Addressing UAV faults ensures mission continuity and improves overall system resilience. Reinforcement learning enables an agent to learn optimal actions through interactions with the environment by maximizing cumulating rewards. In a multi-agent reinforcement learning setting, multiple agents learn simultaneously while interacting with both the environment and each other. Each UAV is modeled as an autonomous agent that observes partial environmental states such as local plume concentration, wind direction and speed, relative positions of neighboring UAVs, its own velocity and energy state. Based on these observations, each agent selects actions such as movement directions, altitude change, or exploration behavior. The reward function is carefully designed to encourage plume detections, source localization, converge efficiency, collision avoidance, and cooperation among agents. MARL approaches such as centralized training with decentralized execution are commonly used. During training, agents share global information to stabilize learning, while during deployment, each UAV operates independently using locally available information. UAV faults and their impacts in real-world deployment. UAVs are prone to fault due to hardware degradation, sensors failures, actuator malfunctions, communications loss, or powerful limitations. A common UAV fault refers to a failure mode that affects multiple UAVs simultaneously or exhibits similar characteristics across agents. Example includes GPS signal degradation or loss, wind sensor malfunctions, reduced thrust due to battery degradation, communication latency, or packet loss. Such faults can significantly degrade plume tracking performance, leading to poor coordination, inefficient exploration, or mission failure. Their robustness to common fault is a critical requirement for practical multi-UAV systems. The problem statement includes the goal is to develop a multi-agent reinforcement learning framework for plume tracking. The framework must handle multiple sources with varying emission strengths. It should also account for common UAV faults that impact sensor reading and navigation. Then UAV fault modeling is common UAV faults includes sensor failures, actuator malfunctions and malfunctions communication disruptions. Fault modeling enables the system to predict and compensate for potential inaccuracies. Incorporate fault scenarios into the training process improves robustness of the RL agent. Next, plume tracking strategy. The agents utilize a combination of gradient-based and probabilistic search methods. Reinforcement learning guides agents to adaptively explore and exploit plume information. Communication between agents allows for coordinate movements and source localization. In real-world UAVs deployments, UAVs are prone to fault due to hardware degradation, sensor failures, actuator malfunctions, communication loss, or power limitations. A common UAV fault refers to a failure mode that affects multiple UAVs simultaneously or exhibits similar characteristics across agents. Examples include GPS signal degradation or loss, wind sensor malfunctions, reduced thrust due to battery degradation, communication latency, or packet loss. Such faults can significantly degrade plume tracking performance, leading to poor coordination, inefficient exploration, or mission failure. Therefore, robustness to common fault is a critical requirement for practical multi-UAV system. The fault-aware multi-agent reinforcement learning to handle common UAV faults, fault-aware MARL framework, incorporate robustness mechanism into learning process. This can be achieved by augmenting the state space with fault indicators or confident measures, introducing chaotic distributions during training to simulate faults, designing reward functions that penalize unsafe or unstable behavior, allowing agents to adapt strategies based on degraded sensing or actuation. By exposing agents to faulty conditions during training, MARL enables UAVs to learn resilient policies that generalize well to real-world fault scenarios. Agents can learn to compensate for faulty teammates, redistribute tasks dynamically, and maintain collective performance even when individual UAVs are impaired. Now, handling UAVs in the RL framework. Fault scenarios are integrated into the reward structure to encourage fault-tolerant behaviors. Agents learn to recognize and adapt to sensor or actuator anomalies during training. Robust policies enable continued plume tracking despite the presence of common UAV fault. Now, simulation results and analysis. Expensive simulation demonstrate the effectiveness of multi-agent RL approach. The system maintains high localization accuracy even under multiple UAV fault conditions. Results show improper resilience and inefficient compared to traditional methods. Cooperative effective plume tracking under faults requires strong cooperative among UAVs. MARL facilitates emergent cooperative behavior such as task allocation, where different UAVs specialize in tracking different plumes. Formation control to maximize area convergence. Information control to maximize area converge to reduce uncertainty about plume sources. Redundancy handling, where healthy UAVs support faulty ones. These strategies allow the UAV team to continue plume tracking even under partial system degradation. For instance, if one UAV suffers from reduced mobility, other can adjust their exploration patterns to compensate. Conclusion and future works. The proposed framework successfully addresses multi-source tracking with UAV faults. Future research will focus on real-world deployment and adaptive fault diagnosis. Enhancing communication protocols and scalability remains a key area for development. Multi-source plume tracking via multi-agent reinforcement learning under common UAV faults represents a robust and intelligent approach to a complex real-world problem. By combining cooperative learning, fault aware decision making, and autonomous UAV control. This framework enables efficient and resilient plume source localization in uncertain and dynamic environment. As AI and UAV technologies continues to advance, such systems are expected to play a critical role in environmental monitoring, defense, and disaster response applications. Thank you for giving this opportunity.